Hi, this is the lecture video for the systematic treatment of equilibrium. It is Chapter 8 from Harris's Quantitative Chemical Analysis, 9th edition. And this specifically focuses in on the last part of the chapter on the methodology and the process for solving a complex equilibrium problem using the systematic treatment of equilibrium. In this video, I'll give a couple of examples after talking about the general layout and how we approach each of the various steps. Okay, so let's take a look here at the systematic treatment of equilibrium, and it is a method for organizing a lot of data for very complex equilibria solutions. So up to this point, we've taken a look at fairly simplistic problems where a single rice table has been able to solve for an unknown concentration given one equilibrium, balanced equilibrium expression and one K value. But we have more complex systems than this. So as an example to get us going, we're going to take a quick look at these chemical equations here for the erosion of statuary due to acid rain. And so, of course, we start this process with our calcium carbonate, which is just limestone. And we can have a KSP for this reaction, and then we also have acid rain, which produces the protons, and we have the product, one of the products of our first reaction is our carbonate ion, which in the presence of our acid rain can be converted to the conjugate base of carbonic acid, which is the hydrogen carbonate. We can write K expressions for both the KSP and for K1. These are not hard to do. And in the end, we can write a total K for this, where we take the products of the two Ks, which is the sum of the two reactions. We can actually cross out a couple of the reactants, our carbonate, top and bottom. But the problem is that we're still, at the end, left with more unknowns than we have information to solve for. And so we need more equations. And as it turns out, if we follow the systematic treatment of equilibrium, we're able to come up with these various equations and identify ways of rearranging them and solving for the concentrations of all chemical species in a given reaction set. And that's exactly what we're going to continue doing here. So first, I just want to set up the steps, the general approach to solving one of these problems using the systematic treatment of equilibrium. So these steps might vary slightly from location to location. We're going to just say that there's 6 steps as I lay out here, and we're going to call these 6 steps formally the systematic treatment of equilibrium. And so this is the systematic way that we treat equilibria problems when a simple rice table won't do. And so first we start by writing the pertinent reactions. In many cases, these are actually given to us. We may need to pull out an extra one or two that we read from the problem, but mostly these will be provided. Then we write a charge balance equation. We'll talk in more depth about this in the following step, the mass balance equations, in just a moment, because these are really the new portion of what we're doing, and they're essential to having a successful solution. Then we write the equilibrium constants for each of the reactions we have, so these are our K expressions, and these just relate to the reactions that we have listed in step 1. Finally, step 5 and 6 really are where we get to doing the solution. So 5, we count our equations and our unknowns, and we make sure that we have at least as many equations as we do unknowns, or else we have to go back to the drawing board and see if there's something we missed. And then in 6 we solve. So I'd like to see you laying out your problems, as you'll see I do, by labeling these steps, just numbering them. You don't have to put any particular labels on them, but making sure that we follow through using all 6 steps in the systematic treatment of equilibrium. We're going to start here first by taking a look at step 2, which is the charge balance equation. And this equation, there's only one of them for each chemical system, regardless of how many equilibrium reactions there are. And this is an algebraic statement of electroneutrality. And it is, in essence, the sum of the positive, all of the cations, plus the sum of all the negative charges, the anions. It takes on the general form that you see below, N1 times concentration C1 plus N2 times concentration C2 plus ... equals M1 times concentration A1 plus M2 times concentration A2, where each of the N terms is the charge of the cation, the absolute value of it, and each of the M terms is the charge of, or the absolute value of the charge of each of the anions. So in this way, we're actually adding up each of the individual charges that exist in solution, knowing that we can leverage the fact that the sum of the cations must equal the sum of the anions in order to preserve electron neutrality. One thing that I want to point out here that I've underlined below is that we always need to remember that we have H2O going to H plus OH minus in every aqueous system. So if that reaction is not listed in step 1, the first thing we want to do is write that reaction in, so we make sure we include it. And then when we get to the charge balance, we want to make sure we include both of those chemical species in the charge balance expression. Okay, so let's actually write out a charge balance for the following system here. It's fairly complex. We have already listed here 6 equations, and you'll notice that the one equation that's missing is the equation for water. And so it's an important thing that we make sure we include that, though what we'll notice is that OH minus and H plus are present. So when we write this out, I identify the cations. Notice we have 2 times calcium because it's a 2 plus cation. We have calcium hydroxide cation. We have H plus or protons, and we have the calcium fluoride cation. The sum of all of those must be equal to the sum of all of the anions. You'll notice here that we have fluoride, we have HF2 minus, and then up top I did add in the water dissociating to form hydroxide and proton. And notice that each of the charges is placed in front of their respective anions and cations with an absolute value. And the sum of all the cations is taken and set equal to the sum of all of the anions. So this equation represents the concentration of the individual cations, not the actual chemical species themselves. So we want to keep that in mind as we work through these statements. I've listed a general form, sum NiCi equals sum MiAi. This is a form of the equation that might be handy to remember. Let's take a look quick at the mass balance equation. The mass balance equation is a statement of the conservation of mass, knowing that we cannot create or destroy it. So we know that if we have a particular chemical species present at the start, it must be present, each of the atoms themselves, we're not doing nuclear chemistry here, so each of the atoms themselves must be present later on in the reaction. And so this is an equation or a set of equations that represent those known mass balances. So what we're saying is that the quantity of all species with a particular atom or group of atoms, maybe a polyatomic ion, that we put into solution must equal all of the species that contain that same atom or group of atoms that are in the solution at equilibrium. And so we just make those statements fairly simply. Now, before we get to the official form of this, or the formal form of it, we're going to write out a little bit simpler case. So we're considering a solution that has 0.2 molar magnesium bromide. And I want to write the mass balance equation just for the magnesium. You see here that we can say very simply that we have 0.2 molar is equal to the concentration of magnesium 2 plus. Now if we consider for a moment what the concentration is of the bromide, we can see that bromide has a concentration of 0.4 molar. We know this because we have 2 bromides for every magnesium ion, so its concentration must be double. Well, if we want to set the 2 halves equal to one another, it becomes relatively simple at this point, because now we can see the 0.2 needs to be multiplied by 2 in order to equal 0.4. So we can do this. We can write in that 2 times the magnesium ion concentration is equal to the bromide ion concentration. And we know that this is always going to be the case, because we know that even if not all of our ionic solid dissolves, when it does dissolve, each of the particular formula units that does dissolve will produce 1 magnesium and 2 bromides. So this is an expression of mass balance that we can write, and we can rely on this to allow us to do substitutions in other chemical formulas and equations that help us solve for a final solution on our systematic treatment of equilibrium. Now, let's suppose for a moment that we actually form magnesium bromide cation in addition to the magnesium and the bromide, and we still have the 0.2 molar magnesium bromide that we're starting with. So let's write a mass balance for magnesium. In order to do this, we know that it's coming from the same source, magnesium bromide, and that all magnesium-containing species need to be accounted for. We also can say that the sum of all of those species must still equal 0.2 molar. Likewise, we can say that for bromine, the similar case, we have 0.4 molar, and we know that the sum of all of the bromide-containing species must equal the 0.4. And then we can combine the two expressions as we did earlier and write that 2 times the sum of all of the magnesium-containing species must equal the sum of all the bromide-containing species. So it's just a more complex form of the same equation we had on the previous slide. Now what I want you to do is I want you to take a moment. I'm going to have you pause the video if you haven't already done this portion, and I want you to try to walk through these next couple of steps in the same fashion that we already have previously. All right, so hopefully you've had a chance to go through these problems. We now have, as I've already started, to write the mass balance for calcium chloride in water, where the species are calcium and chloride. We can write that fairly simply. It's similar to the ones we've written before, where we identify that there must be 2 chlorides for each of the calciums, and therefore the calcium concentration needs to be multiplied by 2 in order to equal the concentration of the chloride. Now I want you to write the mass balance, if you haven't already, for this new, more complex chemical system. Now we can use the 2 inside of the parentheses times all of the calcium-containing species and set that equal to the sum of all of the chloride-containing species. So we see that it's 2 times the calcium plus the calcium chloride cation plus the calcium hydroxide is equal to the chloride plus the calcium chloride cation. Just like we've done before, but we just have new species and more of them. Now we can write the charge balance, and in this case remember that we're pulling the actual charge down. You can see as I've started here, I've pulled down the 2 plus charge, taken the absolute value and said it's 2 times the concentration of calcium, plus the concentration of calcium chloride cation, plus the concentration of calcium hydroxide cation, and proton is equal to the concentration of chloride plus the concentration of hydroxide. I hope you got these correct. If not, make sure you look over them and understand where you went wrong and how you could correct it next time. So let's take now a look at a complex example. We're going to walk through the steps of the systematic treatment of equilibrium in just a moment. But for now I want to take a moment to just continue reviewing steps 2 and 3. So what we want to do is we want to write a mass balance for calcium fluoride. So that's all things that contain calcium and all things that contain fluoride in water if the reactions below are the important reactions. So you've been provided the reactions. I want you to step through and make sure you understand how to get a mass balance. Pause the video for a moment, try to get those, and then I'll walk through it and you can verify that you got it correct. Okay, so let's take a look at this. First of all, it's in water, so we recognize that we have hydroxide and protons present. Next, I'm going to write the general form of the mass balance, where we know that it's 2 times the calcium species is equal to the fluoride species. So that sets me off on a good start, where I can write 2 times the quantity of all of the calcium-containing species I find in the equations above. Then that's equal to the sum of all of the fluoride-containing species. And it's important to note here, we haven't seen this yet, but because calcium fluoride, CaF2, contains 2 fluorides, we need to place a 2 in front of it so that we account for both of the fluorides that are in calcium fluoride. And the same thing for HF2-. Because it contains 2, we need a 2 in front. So note that all of them that contain only one of the chemical species have a coefficient of 1, and each of them that has a 2 has a coefficient of 2. If they had 3 or 4, we would have coefficients to match those quantities as well. Let's take a quick look here at the steps in the systematic treatment of equilibrium in the context of a very simple problem so you can see how they play out before I turn you loose on an example that you can work on yourself. So here we're going to write the pertinent reactions for the ionization of water. Of course, we have H2O liquid goes to H plus OH minus. Then if we try to write a charge balance, we see that OH minus concentration is equal to H plus concentration. We can write a mass balance where we say the same equation. Now this may seem a little odd that the mass balance and the charge balance are the same, but in simple chemical systems we can end up with expressions that are the same. And so we can't count that as two equations, we can only count it as one, but we may find we don't need more than one. So then we can write the equilibrium constant expression. And finally, we can check if we have enough equations for the unknowns that we're left with. We have two equations, which are the Kw expression and either our charge balance or our mass balance. We also have just two unknowns, H plus and OH minus. So in this form, we're able to solve for this with the equations we have using the systematic treatment of equilibrium. Now I'm going to walk through this problem here and show you how to set up the systematic treatment of equilibrium on a more significant or more complex problem, and then give you an opportunity to do the next problem on your own, and then allow you to review the solution as I go through it. So for this particular problem, we start with step 1. We label the chemical reactions and we make sure that they're all present. We see that this is aqueous, and so we have our ionization of water, and we also have the other two chemical reactions that are provided. Next I move on to step 2, which is the charge balance. In the charge balance, we can see that magnesium plus magnesium hydroxide cation plus H plus are the various cations, and hydroxide is the only anion. So we make an accounting of those and write our charge balance equation. For step 3, we're at our mass balance equation. We have hydroxide plus magnesium hydroxide cation is equal to 2 times the sum of the magnesium containing species, Mg2 plus and MgOH plus. So we have our mass balance equation. In step 4, we write our K expressions. I like to label them in my balanced chemical equations so that if I need to come back and verify that I wrote the right one, I know that it's written with the corresponding balanced chemical equation next to it. So our KSP is KSP equals magnesium 2 plus times OH minus squared. Our K1 is provided here. And our Kw, of course, is H plus times OH minus. Now the thing I want to point out here is that I've given you the numeric values for these. If they're not provided, you can look them up in a reference table. Otherwise, it might be that you're trying to solve for one of them. Maybe they become an unknown in a particular problem, but you're given a concentration. Or maybe there's enough equations that you don't need to know all of the Kw or all of the K values in order to solve for them. So we have steps 1 through 4 done. This is the part where we're laying out the information, the data that we have to solve the problem. In step 5, we count up our equations and our unknowns. You'll note here that we have 4 equations. We have 5 equations in this case. We have 3 K equations, and we have a mass balance and a charge balance equation. But we only have 4 unknowns. So we have certainly enough equations. One of these equations will not be used in the end. Now we're going to set it up to solve for it. So first, I'm going to start by simplifying the mass balance equation. If you look at it, you'll note that MgOH plus exists on both sides of that equation. So I can cross out the one on the left and leave just one of them on the right. And I'm left with the expression that I've written here. OH minus is equal to 2 times magnesium plus the magnesium hydroxide ion. Then from K1, I can write that the magnesium hydroxide, if I rearrange this, is equal to 3.8 times 10 to the second times the magnesium times hydroxide. Next, I can substitute. So now I take my simplified mass balance equation and I substitute in my rearranged K1 to get the following expression. Then I can solve for Mg2 plus, rearranging it so that I have Mg alone on the left and hydroxide as the only unknown on the right. I can sub this into my KSP, because notice that my KSP only has hydroxide and magnesium ions. So I end up with the expression I have at the bottom, where the KSP, which is a known value, is set equal to an expression that contains only one unknown. Now, using the solver in my calculator, I can actually plug this in, or I could use other forms of solutions, including plotting it. You can see the form of the equation that I'm going to enter with the numeric values. I'm solving for X, or concentration OH minus in this case. And in the end, I solve it. I find that OH minus concentration is equal to 2.459 times 10 to the negative fourth. This means that H plus is equal to 1.01 times 10 to the negative 14th over that value, which gives me an H plus ion concentration of 4.066 times 10 to the negative 11th. And then I can take pH, which is equal to the negative log of that value, and that is equal to 10.4. So you can see here, if you follow through each of the steps, which I've tried to clearly label and describe my thought process, you can see that I'm slowly rearranging equations, solving them for one variable, substituting that solution into another equation, and working my way through until I have one statement that contains only one unknown. This is the general approach we want to take when we're solving systematic treatment of equilibrium problems. Now I'm going to come to the next problem here. I want you to find in this problem the concentration of silver ion, cyanide ion, and hydrogen cyanide in a salt solution that contains the silver cyanide, and the pH in this particular case is held constant at pH of 9.00. So let's set it up. I want you to take a minute and try to go through step 1, 2, 3, and 4, and see if you're able to come up with the equations and the expressions that we'll need in order to do the solution. In a moment, I'll resume the video, and you can actually see if you got those right, make any corrections, and then I'll give you a moment to go through the solution before we continue. All right, so let's take a look at how we do the solution. In step 1, we identify the pertinent reactions. In this particular case, we're missing water, the ionization that is. So I include that here so I don't forget it. In step 2, it's important to note that actually the pH is fixed in this particular problem. And when the pH is fixed, we can't have a charge balance because we're actually seeing a change in concentrations over time to maintain that pH. But what we can write is that H plus ion concentration must be equal to 10 to the minus 9, and OH minus must be equal to 10 to the minus 5. The mass balance, of course, is Ag plus is equal to Cn minus plus HCN minus. And then we can proceed to write our K expressions. KSP, relatively straightforward, and I have a numeric value for you here. KB, again, fairly straightforward, and I have a numeric value for this one. And then finally KW, which you know, and you know the value for. So now once you verify that you have all of these, we can add up and we see that we have 4 equations, plus we have a couple of the values that otherwise might be unknown, but because the pH is held constant, we know these values. So these aren't held against us. So when we do our accounting here, we have 4 equations and 4 unknowns. Now I want you to take a moment, pause the video, and see if you can figure out a solution, even if it's just making a couple of notes of what you think you might substitute or rearrange first, and maybe you don't actually go through and do the algebra before you play the video. But take a look and see if you can figure it out. All right, so in step 6, we're talking about rearranging some equations. So we're going to start here in my scenario with KB. And I'm going to set this equal to HCN. And then I'm going to place my KB in there, which you'll notice is 1.6 times 10 to the negative 5. And then my hydroxide concentration, as it turns out, is known also, and that's 10 to the negative 5. So the exponents on those completely cross out, and I'm left with 1.6. Then I'm going to sub this into the mass balance equation. I end up with silver in terms of nothing but the cyanide ion. Then I can substitute this into KSP, just like I did in the previous problem. Now I have an expression that has nothing but numeric values and one unknown, which I can solve for using my calculator. I don't even need the solver in this case, because you'll notice that it's just x squared. So I can solve for that by taking the square root of the numeric value I solve for. Finally then, I can solve for the hydrogen cyanide concentration by recalling that that concentration was equal to 1.6 times the cyanide concentration. Then I can take the mass balance equation and place these known values into it to solve for the silver ion concentration. What you'll note is, as we walk through these problems, we'll use the equations that we need to get our first solvable value, and then we may walk our way back through the equations again, substituting in reverse order to re-simplify the equations and solve for other values. In the end, we're able to solve for all of these values, the silver, the cyanide, and the hydrogen cyanide ion concentration. So take a look, make sure you understand the solution. If you have any questions, make sure you come in and ask me in my office.